So further, since all other joints are frozen, both d0 to I minus 1, 0 to I minus 1 and r0 to I minus 1 are constant. So therefore, I get d0 to n dot is equal to r0 to I minus 1 multiplied by di minus 1 to n dot, and di minus 1 to n dot is nothing but, as I said, it's just a pure rotation with all the other links behaving like one rigid body, and that we can write as just qi dot times ki hat cross with di minus 1 to n. So this is just the angular velocity cross product with the position. That's all there is to it. So this would imply again d0 to n dot is equal to r0 to I minus 1 multiplied by plugging that in qi dot ki hat cross with di minus 1 to n and this I would write as r0 to I minus 1 times ki hat cross with, and we just work this out here, r0 to I minus 1 into di minus 1 to n is just this, so this whole thing into on minus oi minus 1. So we simply used the second term in this cross product, which is this. We substituted on minus oi minus 1, and there is still a qi dot that is remaining. So this whole thing multiplied by qi dot. And this becomes then my column in the Jacobian, because this is multiplying the qi dot. Remember, all other qi dots are q dots are 0 except the ith joint, because everything else is frozen. So this is the only thing happening, and this forms the ith column. So this leads me to now the final Jacobian, and that is ith column would be this in case of revolute joint, and we had seen in case of prismatic joint it was just r0 to I minus 1 times ki hat. So putting everything together, we have j is equal to j1, j2. These are the n columns. Remember, the overall j is 6 cross n. So each one of these columns is 6 dimensional, and where the ith column Ji is equal to R0 to I minus 1 by K multiplied by K hat cross with On minus Oi minus 1 and R0 to I minus 1 Ki hat for prismatic, for revolute joint, and Ji is equal to simply R0 to I minus 1 times Ki hat and 0 for prismatic joint. Now this helps us come up with the standard recipe for constructing the Jacobian matrix, and to get all these rotation matrices we will have to revert to using DH parameters and constructing them in a standard way. Once this is done, this matrix, as I said, is extremely useful. It's not only helpful to relate velocities, so really it's V is equal to J times Q dot, or in actually it's V and omega. Just to simplify the notation, I'm just writing V and omega. But beyond relating the velocities, this Jacobian helps us plan smooth trajectories. It helps us derive equations of motion when you are considering dynamics. It helps us in many other places. So it also helps relate torques and forces, which can be a little surprising, but you will see later on that it is quite natural that the same Jacobian will be helping us relate forces and torques. It is also helpful to determine singularities. Now singularities is something that we haven't talked about, but I urge you to go read about it. It's basically some configuration where some configurations from which it is hard to do certain kind of motion. You get stuck in some extreme configurations here or there, and there's a lot more material on singularities and you can go back and look at it. But using Jacobian, you can very quickly determine how close you are to singularities by just looking at the rank of the Jacobian matrix. In fact, at the singularities, the rank drops, which means when you look at this expression, it means that either there are some motions at the joint and nothing is happening at the end effector along certain directions, or it could be the other way around, right? It could be that, this is more apparent when you talk about force and torques. It could be that very small motion or very small torques at the joint can translate to very high forces at the end effector. So there are all sorts of interesting things that you can do with the Jacobian, and we will see that a little bit later on. But for now, this is a standard way, and as I was saying right at the beginning, there are a lot of subroutines and libraries that you can directly use to compute this.